Humanity, we've always looked up, always wondered, are we alone?
Mm-hmm.
And for so long, finding life out there seemed, well, almost impossible.
Right, science fiction, maybe.
Exactly. But things have changed, haven't they? These breakthroughs in finding planets, exoplanets. It feels like we're suddenly getting actual postcards from other solar systems.
It really does. The pace is incredible. We're not just ticking boxes saying planet found. We're starting to see the details.
Which brings us to today's deep dive. We're plunging into the L9859 system, a really fascinating bunch of rocky worlds, and surprisingly close by.
Very close, relatively speaking.
Our mission today is basically to unpack what's new here. There's this big confirmation of a fifth planet, and it's right in a habitable zone. So we want to explore, what does this tell us about how planets form? And, of course, the big one, the search for life.
Absolutely.
And just so everyone knows, we're basing this on some pretty serious research. A new paper pulling data from, the heavy hitters, NASA's TESS, ESO's espresso spectrograph.
And getting insights from Webb now, too, the James Webb Space Telescope. It's a multi-instrument effort.
Okay, let's unpack this then.
Yeah.
Because this system, it really feels like it's giving us one of the clearest snapshots we've ever had of a planetary system nearby.
It truly is. And you mentioned proximity. It's just 35 light years away, which, in galactic terms is practically on our doorstep.
35 light years.
But
yeah, that's close. Makes it easier to study, I guess.
Hugely easier. Follow-up observations become much more feasible. And the star itself, it's a red dwarf.
Okay, red dwarf.
Yeah.
The most common type of star in the galaxy, right?
Exactly. So understanding planets around these stars is, well, it's crucial for understanding how common planets and maybe life are overall.
So take us back. This system wasn't completely unknown, was it? When did we first sort of spot it?
The first hints came back in 2019. That was NASA's TESS telescope.
TESS. Looking for those little dips in light. Transits.
Right. TESS found 3 small planets that way. Then later, using radial velocity, looking for the star's wobble, scientists found evidence for a 4th planet.
Gotcha. 3 from transits, 1 from the wobble. And now this new research, the one led by Charles Cadeau and the team at IRX in Montreal, they've really dug deeper.
They really have. They went back through a massive amount of existing data, archival data, from different telescopes.
So not necessarily brand new telescope time, but squeezing more out of what we already have.
Precisely. That's often where the breakthroughs happen now. It's about the analysis techniques.
Okay, so how do they do it? How do they get this, unprecedented precision you mentioned?
Well, they use a couple of pretty revolutionary techniques. One is this novel line-by-line radial velocity analysis.
Line by line. So instead of the whole light spectrum, they look at individual fingerprints.
Kind of, yeah. It lets them separate the star's own activity, its flares, its spots, all that noise, from the tiny, tiny signal of a planet's gravitational tug. They combine that with another new tool, a differential temperature indicator. And the result was they could essentially see the planetary signals much more clearly. It allowed them to basically double the precision for the masses and the sizes of these planets compared to previous studies.
Doubled the precision. Wow.
Yeah.
And that precision, that's what confirmed they're all rocky terrestrial worlds.
That's right. All 5 confirmed planets fit within that rocky regime based on their mass and size. And yeah, those inner ones are orbiting incredibly close to the star, way, way closer than Mercury orbits our sun.
Let's focus on the first one then, L9859b. You called it a sub-Earth, smaller than us.
Yeah, significantly smaller, only about 84% of Earth's size and roughly half the mass. These sub-Earths are actually quite rare, or at least hard to pin down.
Interesting. And what about its environment, being so close?
Well, that's where the diversity comes in, which is just fascinating in such a compact system. For the 2 innermost planets, so L9859b and the next one out, the data points towards potentially extreme volcanic activity. Think Jupiter's moon Io, but maybe even more intense because of tidal heating from the star.
Wow, volcanic hellscapes right next door, potentially.
Potentially. Then you move out to the 3rd planet, and it's completely different. It has this unusually low density.
Low density. What does that imply? More gas?
Not necessarily gas like Jupiter, but perhaps water. A lot of water. It could be a water world, highly enriched in water, maybe with deep oceans, something totally unlike anything in our solar system.
A water world, next to volcanic worlds, all orbiting the same star so closely. That's wild.
It really is. And another piece of the puzzle. They refined the orbits of the inner planets, found they are almost perfectly circular.
Circular orbits, why is that important? Does it make them more stable?
It helps with stability, but it's also really good news for studying their atmospheres in the future. Predictable circular orbits make it much easier to time and observe transits, especially with something like the James Webb Space Telescope.
Ah, okay. Easier to catch them passing in front of the star.
Exactly. So this whole system, this planetary zoo, it really makes you ask, what does this tell us about how planets actually form and evolve around these smaller, dimmer red dwarf stars? The variety is just striking.
It really is. I mean, you've got potential Io analogs, maybe a water world. It feels like red dwarfs can cook up all sorts of planets.
Yes.
Which brings us to the really big news from this paper, doesn't it? The fifth planet,
Yeah.
L9859F.
Yes. The big reveal, L9859F. And this one's different.
How so?
It doesn't transit. We don't see it pass in front of the star. Its presence was confirmed purely by that radial velocity method, detecting its gravitational pull on the star using extremely precise measurements from HARPS and espresso.
Okay, so we see its effect, not the planet itself blocking light. And the kicker is its location.
Precisely. It orbits within the star's habitable zone.
The habitable zone. Just remind everyone, that's the Goldilocks region, right? Not too hot, not too cold.
Exactly. Where temperatures could potentially allow liquid water to exist on the planet's surface.
And L9859F fits the bill.
It does. It receives about the same amount of energy from its star as Earth gets from the sun. So it's smack bang in that temperate zone, a prime candidate for potentially having liquid water.
Wow. A temperate, rocky world confirmed just 35 light years away.
As Charles Cadeau, the lead author, said, finding a temperate planet in such a compact, diverse system is particularly exciting. It really underscores how varied these exoplanetary systems can be.
So for you listening, what does this mean? It means another target, a really promising one nearby, where we might actually look for signs of habitability.
Absolutely. And René Doyon, another author on the study, he really framed L9859 as a unique laboratory.
A laboratory? How so?
Because it can help us tackle some huge questions in exoplanet science, like what are these super-Earths and sub-Neptunes actually made of? Do planets form differently around these small red dwarf stars compared to sun-like stars?
And the big one for red dwarfs, can their planets even hold on to atmospheres over billions of years, given how active red dwarfs can be, especially early on?
Exactly that question. This system, with its range of planets, offers a fantastic test case. It's like a Rosetta Stone for understanding these common types of planets and stars.
And what blows my mind is, like you said, they pulled a lot of this out of existing data just by getting smarter with the analysis.
Right. Etienne Artigot, another co-author, talked about unlocking hidden potential in archival data. It shows the power of improving our tools, not just building bigger telescopes, though those help too.
So what's next for L9859? Are we going to point Webb at it?
Oh, definitely. The team has already started observations with JWST. Given how close it is, the small size of the star, which makes planetary signals easier to detect, and this incredible diversity of planets, it's a top-tier target.
What are they hoping to find with Webb? Atmospheres.
That's the goal, to study the atmospheres of these planets, see what they're made of, look for molecules like water, methane, carbon dioxide, maybe even potential biosignatures down the line, though that's a huge challenge.
So L9859 joins a pretty exclusive club then, like TRAPPIST-1. These nearby systems we really want to get to know.
Exactly. Alexandrine Leroux, one of the PhD students on the team, pointed that out. It joins that select group, like TRAPPIST-1, that we hope to characterize in really unprecedented detail over the next few years.
So connecting this to the bigger picture, what's the main takeaway? Does this suggest systems like this are common?
Well, it certainly strengthens the idea that diverse planetary systems, potentially including worlds in the habitable zone, could be quite common around red dwarfs, given how many red dwarfs are out there. And that, raises a huge question. Just how widespread are the conditions suitable for life throughout the cosmos? This system is another crucial data point suggesting maybe pretty widespread.
Okay, so that's our deep dive into L9859. An incredible journey, really. 5 confirmed rocky worlds, this amazing diversity from volcanic to potentially watery, and one sitting right in the habitable zone, right next door.
A remarkable system.
And it really highlights how digging into the data we already have with better tools can lead to these profound discoveries. It opens up so many possibilities for JWST and future searches for, well, signs of life.
Couldn't agree more.
So here's something to think about. When you consider the sheer variety packed into this one system, L9859, you've got possible volcanic hells, potential water worlds, a temperate Earth cousin. What does that incredible diversity right there in one place suggest about the sheer possibilities? The chances for life, maybe? Or just completely alien types of geology and climate, forms we haven't even imagined yet scattered across the universe?